This is the 9th installment of the Crash Course Regents Chemistry series, and I am going to review in this installment organic chemistry and all the parts of this unit you need to know for the New York State Chemistry Regents. Let's get started. So organic chemistry gets its roots because we're dealing with chemicals that have a carbon based or have a carbon in its molecule. Carbon is the compound that is central to all organic compounds. So the naming system that we're going to introduce, or at least review today in this crash course series. Remember, crash courses are not meant for initial learning. They're meant for reviewing things you've already learned. However, so the naming system you have learned or will review today is based upon, first and foremost, the carbons, the chain of carbons, okay, that create the organic molecule. So we'll get to that, but let's get to some basics first. So the first and foremost, organic compounds are made primarily, at least initially, from carbons. And you'll hear the word hydrocarbon. And sometimes they'll ask for which of the following hydrocarbons. And I get a lot of students who get this wrong because they forget that a hydrocarbon is just an H or hydrogen and carbon bonded to each other. Alright, so that's very important that when they say hydrocarbons, you're looking for just something. CO2 is not a hydrocarbon. A glucose or sugar, not a hydrocarbon. But all of these chemicals here are organic. This is vinegar or acetic acid. Okay, it's an organic acid we'll get to. This is methane, a natural gas, and often a decomposition of organic matter or even in fossil fuels. This is propane. This is the gas we use in our barbecues. This, of course, glucose, a very simple sugar. And this is CO2 among many. Fatty acids, we have all different, we have fats, oils, all different types of organic compounds. And they have their link, because they're carbon-based, to living or past living, okay, organisms. All right, you should know that fossil fuels that we burn primarily, unfortunately, for fuel or energy in our world, okay, primarily come from the decomposition of past living things. So life as we know it is based because we have this carbon backbone of material that we can add stuff to. So carbon makes nice, strong covalent bonds, okay, but not so strong that it's rigid. So it's primarily a focus of life for carbon backbone chains. So organic compounds deal with past living or current living compounds. Okay, and certainly there's more to this topic than I'm going to cover here, but I'm primarily focused on the curriculum of New York State for the Regents. That's what this crash course is about. All right, so let's move forward. The first thing you have to know is that when we're dealing with organic compounds, you should primarily understand that we're dealing with, okay, we are dealing with things that have nonmetals bonded to nonmetals. So all of my organic compounds that I have drawn here, okay, are nonmetals bonded to nonmetals. And we should know from earlier units that nonmetals and nonmetals make covalent bonds. Okay, so it's very important. Now, why do they make covalent bonds? Well, you should already know from your bonding unit that nonmetals tend to be smaller atoms. And smaller atoms attract their electrons a lot more tightly than bigger atoms. So nonmetals have a high attraction. That attraction we call electronegativity, and I'll just put En here. Okay, so when you have two metals, nonmetals, that attract their electrons very, very tightly or have a high electronegativity, to fulfill their octets, to become stable, okay, in the electron arrangements, they're forced to share because both people, or both, I should say, substances or chemicals or atoms, all right, are forced to share because they both are so strong and attracted for electrons. Neither one of these two, okay, are strong enough to yank the electrons away. Case in point, carbon, okay, has electronegativity about 2.6, and hydrogen is approximately 2.2. So the pair of electrons that exist between a bond and a bond, okay, is right here. Now, it's going to be a polar bond, two different nonmetals, two different electronegativities. They'll be sharing unequally a little bit, according to New York State. All right. Now, this bond, okay, has to be shared because they relatively have high strengths. No one's strong enough to yank the electrons away. So when we talk about organic compounds, we are not talking about anything ionic. Get that out of your little, okay, smart head, all right, or becoming smart head. That's not ionic. For instance, sodium has a low electronegativity, 0.9. Chlorine, okay, I'm writing the number before the element. So if we have chlorine, okay, who has about an electronegativity of about 3, and the numbers have been changing on me, and I believe it's 3.2, there's a huge difference in electronegativity between these atoms. So chlorine yanks the electron away and there's a transfer and we make ions. That's not what we're talking about here. We're talking about covalent bonds exclusively. And because of that, we'll use the term, or you have used the term, molecular. They do not make ions, they make molecules. So what I'm getting at here is the properties of organic compounds are the same properties as molecular compounds, which you should all know is nonmetals. And we know that they're small atoms. They attract their electrons very, very tightly. So if they are solids, you should know they're brittle. Okay? And a lot of these are actually gases because the attractive forces are very weak. But I want you to think of organic compounds as a few different compounds. Think of butter. Think of fat, like lard or animal fat, like grizzle on a steak, I should say. Think of plastics. Think of leather. Think of rubber. Think of gasoline. Okay? These are all organic compounds. And these organic compounds share very similar properties. Number one, okay, they tend to have low melting points. They're not metals, they're nonmetals. Nonmetals have low melting points. Think of butter. Butter melts at a low temperature. Plastics melt at a low temperature. Okay, if you heat your steak up, all your fat's going to drip away. Rubber's going to melt. Okay, so melting points are low. Boiling points are low. And why? Well, because, two, their vapor pressure, how well they evaporate, is high. Look at gasoline. Okay, you're not supposed to have anything, your car should not be running when you're filling up with gasoline, or hopefully no one ever smokes, but if you smoke, you should never smoke when you're dispensing gasoline because this gasoline evaporates very quickly. So you could ignite the vapors. Alcohols that you've learned about, okay, evaporate very quickly. Maybe you've seen demonstrations with those. The vapor pressure, the vapors, okay, can be lit. Okay, you've learned the word volatile. That means something has an ability to evaporate. Okay, so that makes a lot of sense here. So yeah, low melting points, low boiling points, their vapor pressure is high, they evaporate very quickly. A lot of organic compounds are gases, so obviously they're already evaporating. Three, they're not usually soluble. A lot of these organic compounds are nonpolar. So they're not soluble in water. Like dissolves like. So a lot of these, especially fats and oils, you know that they do not dissolve in water. You know, oil and vinegar don't mix because they're a difference. Now there's some organic compounds that are polar, obviously sugar and vinegar, but for the most part, generally speaking, most of these things are nonpolar. So therefore, they're not soluble. And I should put not soluble here. And you know, they are terrible conductors, okay? Terrible conductors of heat and electricity. And you should know that. Why? Because they're molecular. They don't make ions. So they don't make ions, which are free, which is one way we conduct charge. And they don't have any free electrons. Why? The reason why? Because they hold on to the electrons tightly. So they're such terrible conductors, they're good insulators, right? They insulate heat and electricity very well. Think of a rubber. Okay, rubber is a good insulator on a wire because it keeps the charge from dissipating. Why? Because the electrons aren't really free to move that much because they're being held so tightly to the nucleus, nonmetals. It makes sense. Okay, also, they're not electrolytes. Okay, we'll just put that, it's almost the same thing. They're not electrolytes because why? They don't make free ions. They're not ions, they're not ionic, they're sharing electrons. So that's important. And this last one is one that tends to be forgotten. They tend to react a bit slower. Okay, people always forget about nature of reactants. They react slower, by a slow tad, compared to ionic reactions. And this is the rate of reaction, nature of reactants, that you should have learned in Unit 6, Kinetics Equilibrium. Things that are ionic, okay, can react ionically by just moving their charge from one place to another. If I'm an ionic compound, I'm a negative and a positive, I can move away very simply because, well, all I need is something more positive and I'm going to move toward it. Things that are covalently bonded, which are molecular, which are covalent compounds, my friends in chemistry, all right, do not have the ability to just move away. They have to figure out whose electrons go to who. So they react slower. Organic or covalently bonded material reacts slower than ionic compounds. So yeah, so you think of organic compounds, we think of that butter, think of the fat, think of plastics, melt at low temperature, leather. They're also, if they're solids in the solid phase, they tend to be brittle, okay, because they're kind of like, again, attracting the electrons so tightly, okay, kind of like a person with high OCD. They can be broken very simply. So if you have things that are sharing electrons and you apply a stress to them, they can shatter across that line, whereas metals aren't, okay? Any case, those are the basic properties. Now, let's talk about hydrocarbons in general. Okay, now hydrocarbons are generally very nonpolar because of their symmetry. So if I look at methane, CH4, I look at ethane, okay, and I'm drawing something called structural formulas. And you're going to see them in this unit a lot. Now, I'm not going to put the H's in. I'm going to put dashes then. Okay, so this is CH4. This is C2H6. This is C3H8. If you were to count, okay, the H's, you'll see that, okay, that the number of H's equals the dashes. And basically, this is what I call the same homologous series. These are all single bonded hydrocarbons between the carbons. Now, before I get to naming the types of families of carbon bonded compounds, I want to understand something else about these properties. First of all, this is a structural formula, the way that I wrote it here. Now, the way that I wrote it here is molecular formulas. Now, I could write this also CH3, CH3. Now, CH3 is the same thing as what I just drew here. They're both structural formulas. They're showing me exactly how the carbon is bonded to the hydrogens. Here, it's CH3. Oops, I tried to do the same thing. Here it's CH3, CH2, and then CH3 again. Okay, so it's the same thing. These are both structural formulas, and we need structural formulas because structure changes the properties. Okay, and I'll talk about that in a second, but let me get back to properties again. If I'm in the same series, meaning if I have the same type of bonding between my carbons, as I add more carbons and the carbon chain grows, okay, the boiling point increases. So of these three organic compounds, the one with the highest boiling point is the one with the greatest number of atoms or carbons in its chain. So this would have the highest boiling point. Now the reasoning behind that is that things that are nonpolar have something called London forces of attraction. Now in this course we call them weak attractive forces, but they get more significant as you add more electrons. So more carbons to the chain, more electrons, electron cloud is thicker. I know I'm tending to go into a more higher level explanation here, but the higher the carbon chain, the higher the boiling point. That's a Regents question. The attractive forces get stronger. Now, if you have carbon 8, that's octane, right? C8, okay, H18, that's octane, and you know that's a liquid, that's gasoline. If I start getting around C, I don't know, 12, C15 based organic compounds, that becomes waxes. And then C35, I don't know, 72 is asphalt. which is basically a solid. So you can see that these hydrocarbons, okay, by the way, these three are gases, and as we add more carbons, they become liquids, and as I add more carbons, they become solids. So what's happening to the attractive forces as I add more carbons? Well, the attractive forces are increasing so much that they eventually become a solid. Therefore, their boiling points have to go up. The energy it takes to get that maximum evaporation goes up because the attractive forces go up. And by the way, you've learned this already. Higher the boiling point in table H, higher the attractive forces. I'm saying, yeah, higher the attractive forces. So this could be water as A, and this could be acetone, an organic compound, B. And you can see that when the temperature was at standard pressure, 101.3, the boiling point of the acetone was much lower than the boiling point of the water. The water resisted evaporation. This was vapor pressure and this was temperature. Who has a higher boiling point? A does. Why? It has stronger attractive forces. You've learned that. Who has a higher boiling point? The asphalt. Stronger attractive forces. That's why it is a solid. These things are all coming to fruition in a different unit. That's why organic chemistry is taught last. You're just reviewing some of the same principles. Okay, so any case, that's important you know. Higher the number of carbons, higher the boiling point. And by the way, what's the properties of organic compounds? Well, one of them is low melting points. And you know asphalt, okay, has a low melting point. On a very, very hot day, you can watch the road kind of get very soft. So even a solid compound with strong attractive forces, if it's organic, like it is with a carbon, it's still going to have these properties. All right, so let's talk about these structural formulas here. All right, now let's draw two compounds that have exactly the same molecular formula. Okay, I'm going to leave out the rest of my H's here. And I'm going to draw this one like this. Okay, this is called 1-propanol. Now, the 1 tells me the attaching group, which is an alcohol group, okay, is on the first carbon, and they always have to be on the lowest number. And the prop tells me that there is 3 carbons. Table P tells us that that first carbon is a meth, second carbon is an eth, third carbon is a prop. We'll go to table P when we get to formulate some naming in a few minutes. Okay? Now this is called 2-propanol. All right? Now, if you're not quite getting it, let's put in all the H's anyway. Now, these guys have exactly the same chemical formula. Same molecular formula, but different structure. These are called structural isomers. Now, you don't need the structural. In this course, the only isomers you have are these. So these are isomers. Okay, now, what's the chemical formula of each? Well, they're exactly the same. C3, H1, 2, 3, 4, 5, 6, 7, 8, H8, and O. Count over here, it's still C3, H8O. These have exactly the same number of atoms and types of atoms, same molecular formula. In inorganic chemistry is what we learned most of the year. Okay, really, we cared about how many of these other things. It really changed the properties. Since organic chemistry has so many of the same type of atoms in their structures, what we really care about is the structure. And more importantly, structure, I keep saying, is king. You change the structure, okay, you change the three-dimensional nature of how it actually reacts and interacts with its environment. You change its chemical and you change its physical properties. That's right. These two elements that have these two compounds that have exactly the same chemical formula have different chemical and physical properties because their structure is different. Structure is king. Change the structure, you change the properties. Case in point, propanol looks a lot like ethanol, and it would have very similar effects to what ethanol, the alcohol we ingest in our bodies. Not until you're a little older, of course. But 2-propanol, by putting this hydroxyl group, it's not a hydroxide group, it's not a base, okay? When you put this hydroxyl group on the second carbon, this is the first carbon, and the second carbon, that's what this denotes, this goes from being the same effects of ethanol, the alcohol in our wine, liquor, and beers, to something that is deadly. That's right. about 8 ounces of this 2-propanol is deadly, by the Y. All right. So this would probably get you. This you can definitely ingest. This would kill you if you took too much of it. Yet they have the same chemical formula. What's the difference? The structure. The structure. So that's why isomers are important. Okay. Now you'll see a lot of questions that say, hey, which of the following is an isomer? Which one has the same chemical formulas, different structure? It's just that easy. So now we're going to talk about homologous series. I call this the family name. This is the ending name of organic compounds. Organic compounds have carbon, and how they bond with themselves in a carbon chain that gives it its organic nature, okay, changes its properties as well. So we start naming these organic compounds by how the carbons and how many carbons we have together. So we have to identify what type of homologous series we have. Homo means same, series is really the family name. It's based upon the bonds between the carbons. Now, table Q gives you this information, but I kind of like adding to it or writing as we go to learn. So alkanes have single bonds between the carbons, which means they have the ability to bond with more H's. Every carbon has to make 4 bonds because carbon has the electron configuration of 2-4. As we've talked about in other places, you need to have 8 electrons for it to be stable, so it needs 4 more electrons to bond with. So to pair up with its 4 valence, it can make 4 bonds. Okay, so carbon must always have 4 bonds in our structure. Since there's only a single bond between the carbon here, this guy holds the maximum amount. So this is C2H6. Now, in table Q, they give you a general formula. And it goes, if you're an alkane, it follows CnH2n plus 2. What does that mean? That means if you're an alkane, if you're single bonded between the carbons, okay, if you're an alkane, the number of H's is related to carbons by this formula. Case in point. If I've got 2 carbons, that means I have a 2 here. 2 times 2 is 4, plus 2 is 6. This means if I've got a 2-carbon hydrocarbon, it's an alkane if I've got 6 H's for the 2. If I've got 3 H's, if it's C3 and it's an alkane, well, I double the N, or the number of carbons, 6, add 2, that'd be H8. And look how that works out. C3, H1, 2, 3, 4, 5, 6, 7, 8, making sure I have 4 bonds for each of the carbons. All right, so it works nicely. So it's a general formula that you can use to identify, hey, if you've got a single bonded hydrocarbon, which would be called the alkane naming, the alkane family. All right, so it's important that you can be able to use that. It's a nice, easy way. Now, what's special about alkanes, unlike the other 2 that I'm going to discuss, is these guys, okay, are saturated. They're considered to be saturated hydrocarbons. So I'll put it right here, saturated. And what are they saturated with? They're saturated with hydrogens. There's no other homologous series or family of hydrocarbons that can hold more H's per the number of carbons they have. This has the greatest number, so this holds the maximum. Now these guys here are unsaturated, and the reason? Well, because they have multiple bonds between the carbon, they have to have less H's. For instance, okay, let's get this red line out of the way here. This alkene has 1, 2. Well, remember, carbon has 1, 2 bonds already, so this is 3, 4. So my friends in chemistry, this compound can only hold 4 H's. So it's C2H4. Its general formula listed in table Q, I'm not making this up, you don't have to know this, is given as CnH2n. Notice we lose or drop the plus 2. Why? When you add a bond between the carbon, you lose 2 H's. Okay, so it's always double the amount. Look at that. This is a 2 here. Okay, so the 2n is double that, 4. So if I have 4 carbons, guess how many H's I need? Double that, 8. So every time you double the H's to the carbons, you know you're dealing with an alkene, something with a double bond. Simple stuff there. Okay? And of course, this is termed to be Unsaturated because it's not holding on to the maximum. With 2 carbons, I should have 8 hydrogens if it was saturated, but because of the double bond, it holds less H's than possible, so it's unsaturated. And if you're an alkyne, you have even less H's. With a triple bond between the carbons, okay, you only have room for 1 more H. So your general formula, or let's write the chemical, C2H2. Look at that, we're going down by 2 H's every time. And the general formula is CnH2n minus 2. We're losing 2. Again, these are all listed in table Q. All right? So again, the saturated or the unsaturated compounds you have to know, very important core understanding, are the ones with multiple double bonds. The saturated are the ones that are holding the maximum. Now, how do we use this in naming? Well, when we name something, we start with the hydrocarbon longest continuous chain. So we're going to go to table P for a second. So when we start naming these hydrocarbons, we use the prefix in front of the homologous name. So this meth is 1 carbon, eth is 2 carbons, prop is 3 carbons, but is 4, and so on. So we identify the name by how many carbons. Okay? And of course, table Q, as I've just talked about, gives you the general formula and gives you the alkanes. Notice the example they gave us, which is the same examples I used just now, ethane. Eth is how many carbons? Well, if you look on table P here, eth means 2 carbons, so it starts with an eth. All right? And if we look down here, because it has single bonds between the carbons, it ends in ane. And of course, the rest of these below, the unsaturated hydrocarbons here, are ethene and ethyne. Why? Well, eth because they still have 2 carbons, but ene because of the double bond, and ine because of the triple bond. Okay, so very straightforward in naming a hydrocarbon. Except when we deal with these guys, we have to tell the person who is reading our name where these double and triple bonds are. For instance, again, dashes represent H's. Now notice this has 1, 2, 3, 4 bonds, 1, 2, 3, 4 bonds, and this carbon has 1, 2, 3, 4, 5. I drew this incorrectly. You have to, when you draw these, make carbon have the right number of bonds, which is 4. So this is a hydrocarbon that is in the alkene family. How we name it? 1, 2, 3 carbons. That's a prop. Prop is for 3 carbons. And it's an ene because it's double bonded. However, where is that double bond? Now, I probably don't have to name this one, but we'll just do it because this is on the first carbon. So this is 1 propene. Let me say, well, why do we have to put the number in front? Because you got to tell me where the double bond is. Remember, structure is king. Change the structure, change the properties. Now, let me draw a better example. So if I've got this compound, okay, 1, 2, 3, 4. 1, 2, 3, 4. These guys only have one room for 1 H. And this is 1, 2. And this is 1, 2, 3. Now, this is 1, 2, 3, 4, 5 carbons. So this is a pent from table P. You can look it up. Now, on the second carbon, if I count this way, 1 carbon, 2 carbon, I have a double bond. So it's a pentene. But on the second carbon, I got a double, so I put 2 pentene. Now you could have said, well, isn't it 1, 2, couldn't it be the third carbon if I count this way? Well, the naming system that I'm going over helps us figure out the structure, and it's based on the attaching groups, or the differences, always get the lowest number. So by convention, they decided that when you're naming carbons, things that you want to identify have to have the lowest number. Okay, so this is 2 pentene and not 3 pentene. All right, now if it was 1 pentene, the double bond would be over here, and you change the structure, you change the properties. So organic naming is about the structure, okay? And if you have the structure, you should be able to get the name. Or if I give you the name, you should be able to write the structure. For instance, if I gave you 2-hexyne, okay, well, hex tells me there's 1, 2, 3, 4, 5, 6 carbons, right? Hex is from table P. The ine tells me there's a triple bond. And you would say, well, where do I put it if I didn't give you a number? Well, I'm saying on the second carbon, there's a triple bond. Everybody else has to have one bond. Fill in the H's so that everyone has 4 bonds. Notice this one won't have any H's. Neither would this one because of the 4 bonds. And this would be 2-hexyne. You'd be able to go back and forth. Now, we have attaching groups that also are carbon-based. Let's quickly go over those. Okay, now we're looking at this structure here, 1, 2, 3, 4, 5. It's saturated, it's an alkane. Now some people would say, well gosh, this must be 1, 2, 3, 4, 5 pentane, right? I got 5 carbons, single bond, I'm doing great. Nah, that's wrong, okay? Because when you figure out that parent name, it's the longest continuous chain of carbons. Careful with that. So this is 1, 2, 3, 4. 1, 2, 3, 4, the longest continuous chain. So I'm counting my chain of hydrocarbons to be right here. So this is a 1, 2, 3, 4. Table P tells me this is a bute. Now, there is an ane because there's single bonds, but there's something attaching to my carbon chain, and it's a 1 carbon group. And we say it's a methyl. Oops. Methyl. We add the YL to make it sound cool. So this is a methyl butane. And if I put this down, this would be wrong too because I need to tell me where it's located. It's located on the 1, 2 second carbon. So our naming system's starting to get longer based upon, okay, what's attaching to the chain. And if you look at your shampoo bottle at home, next time you bathe or wash, that could be a month or hopefully soon, you'll see these names in the bottles which are organic with numbers and dashes, and they get pretty long, okay, because they're defining the structure. All right, so this is 2-methylbutane. All right, and in any case, we need a number for where it is. Let's do some others. Okay, let's do a halocarbon. Let's do this. Let's have this guy. And let's put a chlorine here and a chlorine here. We're going to fill in the rest with the H's. Okay, I'm going to name this now. 1, 2, 3, 4, 5. So it's a pent from table P. It's a pentane. But it's not just pentane. I've got chlorine groups. Now, what do I name the chlorine groups? Well, halogens have a name for these. Table R is your friend. Now, table R gives me fluoro, chloro, bromo, iodo, okay, as the functional group names. And they actually give me an example. 2-chloropropane. What does that mean? I have a propane. How many carbons? 1, 2, and 3. On the second carbon, which would have to be the middle carbon since it's 3, I have a chlorine attached. It's just that simple. Ane means single bonded. In this example, though, I have got 2 chlorines. And if you've got 2 of something, we use a di for 2. If it was 3, we'd use tri. You won't see 4, but that'd be tetra. So in this case, where's my chlorines? My chlorine's either on the 1, 2, 3rd, and 4th. It could be the 3rd and 4th. Or if I count the other way, it could be my second, right? Counting this way is the 1st carbon, 2nd carbon, the 3rd carbon. So I can either go 2 and 3 or 3 and 4. You have to pick the lower number combination. Attaching groups, like the double bond, have to go on the low number. So my friends in chemistry, we would say on the 2nd and 3rd carbon, we have 2 chloros. So we would say 2,3-dichloropentane. And if I was to put a chlorine here, okay, that would be 2,2. Got to have a number for every attaching group. 2,2,3-trichloropentane. Okay, and that's as tough as it's going to get. All right, and again, if you're having trouble naming these, you can look at my other videos, instructional videos that are more detailed, but we're going to move forward. Okay, so we have homologous series, which is the bonding between carbons that changes the ending name. I call it the parent name, the last part of the naming. Now, functional groups make some adjustments to that. Functional groups are basically a different kind of arrangement on that carbon chain. So you have a carbon chain, but you've got some arrangements of either of usually other atoms in a particular way that give it some very similar properties. Okay, so functional groups are a different arrangement of some types of atoms, nitrogens, oxygens, or halogens in a certain way on the carbon chain that give it some unique properties or very similar properties within that type of unique arrangement. So in table R, they give you these general formulas and people struggle with these. These are the arrangements. For if I have a halogen, this R means the rest of an organic compound. So if I've got CH3 and I've got a Cl attached, that's going to be chloromethane, right? One carbon, single bonds, methane, and chloro in front. So it's a halocarbon, okay? And it's listed in table R. Now, if I've got the rest of an organic compound, I've got a hydroxyl group. By the way, this is not a base. Like this, if I have C2H5OH, okay, this is an alcohol. Now, we name this by using the OL ending. What's nice about table R is they give an example how to name this. 2 carbons, eth, everything we just learned. It's single bonds between the carbons, so it's ethane. We take the E away and we add OL. Okay, you could say 1 ethanol because there's 2 carbons, it's not going to change. If I had a 5 carbon compound, okay, so if I had 5 carbons and I had the OH in the middle, the rest have the H's, okay, this would be not ethanol, it'd be pentane. Take the E away, add the OL for the alcohol, and on the 3rd carbon you've got that. Again, you don't have to memorize, let's go to table R. And you should feel lucky and privileged that you have to not memorize these, because at one point before they changed the Regents a few years ago, many few years ago, it's getting faster in time I guess, you had to know this by heart. So alcohols are the rest of an organic hydrocarbon plus an OH. Look at that, they give an example, the OL. So look at the example, propanol, 1, 2, 3. On the first carbon, there's the hydroxyl group. And I can't say this enough. They love to add these things with bases. This is not a base. It's not an electrolyte. It does not break apart into ions. These are organic or covalent bonds. Okay, look at an ether. Okay, an ether, look at the general formula. On either side of a single bonded O, I've got an ether. And they gave you how to name it. You name everything around the O. It's a methyl group, a 1 carbon group, the YL to make it fancy. And you have a 2 carbon group around the O. And there's your ethyl, so methyl ethyl ether. And if I was to draw it as CH3, OCH3, I have 2 what? Methyl groups. We go with this dimethyl ether. Okay, so again, they give you the example, they give you the general formula. All they expect you to do is be able to identify it. Okay, aldehydes, okay, have a CHO at the end. Sometimes I call this the Chomama series. Okay. It's an ending series. Why it's an ending? Because you see the R at the end. See, an ether is a middle series. Look at that. If you've got an ending with that compound, now sometimes they show the bonding, sometimes they call it CHO at the end, and it's an aldehyde. Look at the naming system. The example is an al. Prop for 3 carbons, ane for single bonds between them, the al for that group. That's all you have to know to be able to identify that. Okay? And ketones are a lot like aldehydes. They're kind of like a carbon double bond to the O, but in the middle, look at this. R and R prime means the rest of some organic compound, and then what? Rest of another organic compound with a carbon in the middle. Notice it ends in -one. Look at the example they give you, -one. Notice they tell you it's a 2-pentanone. Pent is 5 carbons. Ane is single bonds between the carbons. Don't fall in love with this double bond, think it's an ene. Enes and ynes are between the carbons. So a double bonded carbon to an O in the middle of a chain is a ketone. Here's an example to wake your mind up to do that. A double bonded to the carbon at the end is an aldehyde. Notice aldehydes don't have numbers because they're always at the end. Then we have organic acids. I call these the Q groups. A lot of times you'll see COOH, organic acid. By the way, it's not the first place you've seen them. Let's go to table K, and K lists your what? Acids, which include an organic acid. There's your Q group. Okay, ethanoic acid, oic acid. Let's go back to our other table. Now they gave you ethanoic acid, but my friends in chemistry, that is an organic acid. It's an oic acid. Now, how do you name them? The ethanoic acid they gave you must have had just 2 carbons, which, by the way, is vinegar. The example they give you is propanoic acid. 3 carbons, prop, and there's a COOH ending. So, okay? Now, organic acids are very special. They love to pick on these because of all of your organic compounds. This is the one that is an electrolyte. This makes free ions. Why? Why does it make free ions? What do acids do? Acids dissociate into protons, or they make H3O pluses in solution. They lower the pH because this increases. They're producing ions. So because of that, these are the only ones that will conduct electricity, and sometimes they pick on organic acids because of that. So if you find yourself in a scenario and you find yourself a coup and you don't know what the answer is, chances are, as the song goes, it will be an organic acid. Okay, very important. Now, esters. I want to go back to esters. Let's go down to amines and amines. Amine, your own business, is just a what? A nitrogen attached to some organic stuff. Look, an N attached to a carbon chain. How do we name it? Hey, this N is called an amine. Where is it located? On the first carbon. So for 1-propanamine. Propan, because it's prop is for 3 carbons, ane single bonds, and the amine is for the N. Now, an amide is very similar but different, but the functional formula will help you. You have an N bonded to the rest organic compound, and then this N is bonded to a carbon double bond to an O in the middle of a compound. So there it is, an N bonded to a carbon who's bonded to a what? A double bonded, and that makes it an amide. How do you name it? How many carbons? Prop, single bonds between the carbons. Ane, take the EUA, add amide. Okay, these are the examples. You don't have to know them by heart. Know where to look. Let's go back to the ester. Okay, this has some more implications that the other ones do not. So let's spend some time with an ester. Now, this ester, okay, esters have a general formula of a carbon double bond to an O like a ketone, and then an O single bond like an ether added together. All right. Now, esters are picked upon just like organic acids because esters are the aromatic compounds. These guys are responsible for all the sweet smells in nature. So all the nice floral smells or fruity flavors, because smell and flavor kind of go together, are due to the esters. So flowers and fruit smells and sweet smells of nature are due to the workings of esters. So that does pop up. But they also pick on the ester of how to name it and what makes an ester come together. You should know that an ester is made from the organic acid that is used to make it and the alcohol, and the naming system comes from that. So this is methyl propanoate. Let me show you how methyl propanoate is put together. Now, methyl propanoate means that I took a methanol, CH3OH, okay, and if you don't like me to draw it that way, I'll draw it the other way. A methanol is this, and I added, or it reacted with, an organic acid, a Cu group, that looks like this. And this was prop, so 3 carbons here. And this organic acid is named as an oic acid like table R. It's an electrolyte like we talked about. So this is methanol. This is propanoic acid. And again, if you need to review the naming, you just go to table R and it gives you an example, oic acid. The propane part we know about, we just went over that. Now what's going to happen is, when these guys collide, what's going to happen is the water is going to come out. So water comes out. And once the water, they call this the dehydration synthesis, I can speak. When that comes out, these guys come together. So the CH3 comes together. I'm left with an O. This water is now gone. So this part of the molecule comes together. Carbon double bonded to an O. To another C, to an H, and there we go. And there is my organic acid. I'm sorry, here is my ester. And this came from the alcohol, and that's the CH3, O, carbon double bonded to the O, and then I have the CH2 and the CH3. This is an ester. Notice there's my ester part. The general formula is what? R to some O, double bonded to another O to another R. It's the middle of a compound. How do I name this? Well, you take the alcohol that made it. It's methyl, YL again. And the acid that made it was propanoic acid, but we use propan OATE, O8 to name it. Very simple. So when you look at an ester, you have to be able to figure out, hey, what acid and alcohol was used to make it, and this is how you do it. Okay, you split the O's down the middle. The one with a carbon double bonded to an O had to come from the acid side. Only organic acids with the general formula of what? C double bonded to an O to an OH to an R have a double bonded O. So this was my acid side. This is my alcohol side because it doesn't have a carbon double bonded to an O. So that's how we name it. The alcohol side, you name it by how many carbons. The acid side, you find how many carbons on that side, and you add the OATE. Okay, just like table R shows you. Now in table R, they drew this opposite of each other. Okay, so if I just erase this, maybe. Okay, they drew it opposite. If you notice, they had the alcohol side on this side and the acid side on this side. How do I know? Split the O's. The carbon double bond to the O is the acid side because guess what? Acids have a double bonded O. The side with the carbon on the other side of the O that doesn't have a carbon double bonded, it has the alcohol side. Why? Because the alcohol side doesn't have a carbon double bonded to the O. So I don't care how they write it. Find the alcohol side. Find the side of the two O's that does not have a carbon double bond to an O. That's your alcohol side, and you name it in front. We'll do one more example. Okay, I want to name this, which means I have to identify the acid and the base. I'm sorry, the acid and the alcohol that makes that. Now, before I forget, I probably forgot to add that when these came together, water came out, and it made the what? Ester, and also made water. And this, by the way, is the first reaction we go over, and it's called esterification. An alcohol and an acid, the water coming out makes the esters called esterification. Okay, it's very important you identify that. Now, back to the naming this. First thing I do is I'm going to split the O's. Who's got the carbon double bond to the O? The acid side does. Who's the acid? Because they could say, what's the acid that makes it? Well, meth, eth, prop, bute. Butane, take the E away, add oic acid. Butanoic acid makes this ester. What about this side? This must be the alcohol side because it does not have a carbon double bond to an O. So this is a alcohol side. So this is ethanol was used to make this. Okay, and what is the name? Take the alcohol side, eth, add YL to make it fancy. And this is 1, 2, 3, 4, butanoate. All right, which I think might be the pineapple flavor or smell. I could be wrong there. Okay. All right, so now we're into the organic reactions, and most of these reactions you just have to be able to identify. We just left off with naming esters, so that's the esterification reaction where we have an organic acid and alcohol come together, the water comes out, dehydration, synthesis, and we create the ester. Okay, name of the ester? Well, the acid is meth, prop. So this is going to be propanoate at the end because I changed the acid to that OAT ending as table R. And this is the methanol, so this is going to be meth with the YL, methyl propanoate, okay, which is a fruity smell, I think. Now, that's just a reaction. You have to be able to identify that esters are made from acids and alcohols and water comes off, and they call it esterification. That's the aromatic sweet smell compound esters are made. Okay, substitution. Substitution is one they pick upon. You start with a saturated hydrocarbon. Let's start with an ethane, okay? So we'll draw propane, which is saturated, C3H8, C and H2N plus 2. Okay, now if I want to add, let's see, chlorine 2 to it, what's going to happen is, well, there's no room to put chlorines on here. So what's going to have to happen is an H has to substitute with a chlorine. And what we're going to make, okay, is we're going to make this compound with a chlorine attaching to, I don't know, one of these chlorines. We don't know for sure which one exactly it would be, but one H had to come off. Okay, so this red H had to come off and hook up with the chlorine. And notice I have two products. I have this compound, we should be able to name. It's 1-chloropropane and hydrochloric acid. So in Cl, remember it's a Cl bonded to Cl, one Cl came off and one H had to substitute to add the chlorine because it was already what? Saturated with H's. There was no room. So substitution, okay, is when you take a saturated hydrocarbon plus a halogen, one comes on, one comes off to make room, and you have two products. Okay? Now in an addition reaction, everything adds because you're dealing with something that is unsaturated, which means it can hold more atoms because it's got room. For instance, if I was to draw you this compound, okay, this is 1-propene or propene. Notice it ends in an ene, okay? Now, this has less H's, so it's unsaturated. And the reason why it's unsaturated is because it's got a double bond. Carbon must make 4 bonds, so there's less room. So now, if I've got chlorine 2 again, what the chlorine 2 will attack the double bond. And what will it make is, well, it'll open up this double bond and it'll allow the carbons to be able to attach itself to 2 more positions. So these blues are what were there, and by opening up the double bond, now I can add, okay, a chlorine here and let's say a chlorine here. So I've went from something that goes unsaturated and now it went saturated. And notice I only have one product. One product. Why? Because everything added because there was room. Now, another type of addition reaction is when you have an alkyne. If I had this compound, put in the H's, notice I only have room for this many H's because there's even less H's because there's more bonds between the carbons. Carbon must have 4 bonds. Now, I can take 2 chlorines here, and they can completely add to this chain, and this would look like this. Open up that triple into a single, okay, and what you're going to add is you're going to be able to add 1, 2, 3, 4 chlorines to this and make a saturated compound as well. Okay, but something you should know is that the chlorines add to different carbons. Okay, for instance, in this one I had here, notice I have a new position only on different carbons. So that's going to add on 2 different carbons. So that's addition, okay, where everything adds. You only have one product. Substitution, you have to have 2 products as one thing has to come off to come on. The fourth one is fermentation. You just have to be able to identify it. We're taking a sugar and we're going to ferment it with some yeast. And the enzyme in yeast, sometimes they mention by name, is zymase. And what it does is it produces energy from the sugar and it produces 2 byproducts. Ethanol, eth for 2 carbons, ane for single bonds, OL, and of course carbon dioxide. And this fermentation process, by using the anaerobic process of how yeast get energy without oxygen, anaerobic, okay, this byproduct is what we use for our wine, our beers, and our liquor, okay, or for industrial processes for having an alcohol. But the bottom line is we get our alcohol that we consume by fermenting a sugar, whether it's grape or for wine, barley for beer, or grain for alcohols or liqueurs, okay? Whatever it might be, this is the process. You just have to identify it. Notice in some processes we want the CO2, like in beer. We don't want it in wine, okay? Champagne does have it. We don't add this after the fact. It's a product of the process. Okay, so you just have to identify a sugar, okay, plus the yeast or zymase makes ethanol. That's all you got to do here. This reaction, of course, is combustion, taking an organic fuel like methane plus oxygen makes CO2 and water. We've talked about combustion at length. It's exothermic. By the way, it's also a redox reaction. There's a zero, but there's combustion by name. And now we have polymerization reactions. Polymerization reactions, we take something called a monomer. A monomer is for instance, in Teflon, okay, we have carbon double bonded to carbon. And if you notice, carbon makes 4 bonds, so it only leaves this many F's available. It's unsaturated with F's because of the double bond. Now this is the monomer, and this can repeat. So this monomer, okay, can react with another monomer, okay, and make a polymer, which is a repeating unit. Okay, so how does that occur? Well, if you've got a double bond, we open up the double bond and this can add directly. And we call this addition polymerization, just like the addition reactions I showed you before. So if you go up the process, we're opening up a double bond like we did in the addition reaction because it's unsaturated. The monomer is. Okay? So this would make a long chain polymer. It repeats over. It'd be a carbon bonded to a carbon, bonded to a carbon, and this would repeat. That's why they call it a polymer. So you're making a long chain, and it'd be these F's, many of them. Not going to keep drawing them, but you get the idea. And this is Teflon. And this is an unnatural, okay, polymer. It doesn't really occur in nature. You should know your natural polymers to be starch. Okay, starch. I can spell starch. Okay, or is basically sugars attached to each other in a certain angle, okay, at beta bonding, I believe. In any case, you have glycogen, right? Glucose, glycogen stored in the liver. You have peptides, or you have proteins. Proteins are what? Proteins are made of amino acids that have an amine group and an organic acid, okay, and they come together. With many, many amino acids. And you have your unnatural or your artificial or unnatural polymers. And that could be nylon. Okay, it's not made in nature. By the way, you also have the silkworm. From the silk is also a natural polymer. A lot of your unnatural polymers that we make are the plastics. Okay, they don't really have plastic trees in nature. We have a rubber tree in nature, so a rubber could be considered a natural. Also, for unnatural or synthetic polymers, nylon, plastics, Kevlar, that's that bulletproof stuff, Mylar, okay? Any case, polyurethanes, shellacs, these are all things that don't come from nature. We make them, and of course you should be able to identify the ones that do. So addition polymerization is taking basically a monomer and you're opening it up. Now we have other types of polymers, and let's do that one too. We have something called condensation polymerization. Now, condensation means that water, okay, is arriving. So sometimes we put monomers together and water comes out. So if I've got a organic acid ending, okay, to some, I don't know, and it's some repeating unit here, and I have an alcohol part, right, a C to an OH, which leads to, let's say, another Q group at the end. Well, guess what? Water comes together, and by the way, you're going to make a what? An ester. And this would be a polyester. And these would come together, and you could see that you'd have this end for another. So this would be the monomer right here, which is basically an alcohol on one side and an organic acid, and that's how these would be built. So if the monomer, let me make this nice and clear and understandable, is CH2 and then a CH2 with an OH at the end, okay, you can see how these guys would fit together. Water comes out because, again, it's a condensation polymerization, or it's a dehydration synthesis. And by the way, this is making esterification, an acid end and an alcohol end. So polyesters, as we talked about, are made by making ester links, and water comes out, and this thing would keep going. And a lot of the polymers are written as a bracket. Whatever chemicals they put in here, they put a bracket to some number of n to show that that's what's repeating over again, so you can identify that you're making a polymer that's repeating. Well, saponification is our last one, and one that comes up infrequently, although we did see it, I think, last year. Saponification is basically the making of soap. What we take is we take a triglyceride, a stored fat. We have our glycerol molecule bonded in an ester link with 3 fatty acids. Now, 3 fatty acids, my friends in chemistry, are just carboxylic acids at the end, and you have these long chain hydrocarbons that repeat over and over again. Okay? And so basically, this is made by, triglycerides are made by fatty acids, which are organic acids, and this glycerol molecule, which if you remember is a trihydroxyl alcohol that has 3 OHs in it. And what we do here is when you make a triglyceride, guess what? The organic acid with the alcohol makes an ester link, and there's your ester. So when we store fat, okay, the fatty acids react with the glycerol to make triglyceride, which is right here. Okay, so saponification starts with a triglyceride molecule. Okay, and that can be written like this: C17H35 COOH. We're going to parenthesis here with 3 of them because that's just showing the fatty acids, I guess, bonded. H2. Okay, and then what we're going to do is we're going to add a strong base, NaOH. The strong base is going to, basically the hydroxide is going to cleave this, okay? When it cleaves this, okay, all right, it's going to make, I guess I did that kind of incorrectly, all right, it's going to cleave, all right, this link here and it cleaves this link right here, and what it does is it's going to produce 3 compounds that are basically look like this. The ending looks like this, O negative, and you have that CH2 that repeats over again. Okay, how many times? So you're going to make 3 of these, and the Na plus that dissociates away from the strong base attracts to the positive here. And what you're going to have is a very, very non-polar tail to this, and a very polar end here, and that's a soap molecule. Soap molecules have a hydrophobic, okay, water-fearing air, non-polar, and water is polar, so this is going to react with the fats, because fats are non-polar, and this part is water-loving, philic. It's going to go with the water, so we call those micelles. So if you have a fat molecule, all right, a glob of fat, water is never going to attract it, so it'll stay on your skin. But what will happen is the soap molecules with their non-polar tails will get in here and attract it, and with their polar heads, okay, be able to interact with, let's say, water, and water can attract these and pull the whole thing away. And that's how soap works. The polar end, okay, is right here, and the non-polar end is that hydrocarbons that are very symmetrical. So all you really got to do here is identify that you have a triglyceride, and that 3 kind of gives it away. And you should know that it's going to break apart into, all right, 3 of these soap molecules, and so you'll see something like 3. So it's going to cleave that triglyceride, and I'm making, we're just making up some C17H, depends on how long the fatty acids are, and you're going to have this COO negative ending with the Na at the end. And of course, you're going to recreate the glycerol. The glycerol I can write as H2 and then CH OH and 3. So all this is the glycerol. Now, rewriting the glycerol means, okay, you're having the 3 carbon with the OHs. So you're making the trihydroxyl, the glycerol compound. That's what really Sorry, that's right here. That's what this is right here. So it's going to be that fat molecule here, which is nothing more than these 3 ester links. When you add sodium hydroxide to it, okay, you're going to break it apart. So let's make this a little cleaner up. Let's clean this up a little bit. So here is saponification, and you don't have to be able to write this out from scratch. Just identify it. Here's my triglyceride with the ester links. It gets cleaved by the base to make 3 soap molecules, and of course replenishing and recreating the glycerol, the trihydroxyl. So that is essentially the organic chemistry unit in a nutshell or in a video. I hope you enjoyed, and these are the things you have to know. Take care.